So here's the deal. All a digital computer is a finite state machine that can sequentially walk through a memory, a digital memory, and read out numbers, interpret those numbers as instructions to do something after decoding that instruction, and then read out the next instruction. So it's a series of sequential instructions, normally written by a human being, at least in our case, although someday it will probably be written mostly by computer. And what can an instruction do? Well, instructions can add, subtract, and or invert. You can do a bunch of mathematical operations. That's pretty standard on one or two operands. It can move data from one place to another. So typically there's a memory that you use to store data in, and it can access any location in that memory to put data into it or put data out of it. Well, what's that for? Well, you might be taking data out of it, adding it, and then putting the result back in the memory. It can normally move data out to the outside world or read data from the outside world into the computer. So you can use that to either see what somebody is trying to ask you to do externally. They're pushing a button. They're telling you what the temperature is. You get sensor information that can be almost anything these days. Or you're outputting data to turn on lights, make motors run. We saw that in the second lab, we made we were able to output data that made an LED go from top to bottom and put different colors on. So we can move data around, we can operate on data. The other thing we can do that's really important is we can make decisions. We can compare things. Is the data equal to 0? Is it bigger than another value? Without that alone isn't super useful, but we can also change the execution from just sequential instructions and jump to some other instruction, not the next instruction, based on whether, some comparison is true or false. So given those three things, we can do pretty much anything. Move data around, act on data, and do comparisons and change our execution based on those comparisons. And that's all there is in a standard computer. We typically have some memory called the program memory. We typically have some memory called the data memory. In modern computers, those are combined. It turns out that the computer that we're using in the Arduino, they're not, but it's all hidden from us. Programming a computer traditionally, when you first create it, is kind of hard because everything in it is a number. The programming instructions are numbers. They're interpreted as actions. The data are numbers. They can be interpreted as binary numbers, 2's complement numbers. They can be interpreted as floating point numbers because as long as we have a bunch of 1s and 0s, we can say they mean almost anything. They can mean a mantissa. They can mean an exponent. Doing that in binary is really tedious. So of course we have higher level languages. Originally we had something called assembly language, which was just 1s and 0s with some human readable mnemonics that made it easy. So instead of having to use a number like 1001110 to say add, we could say ADD. That still was kind of tedious. So now we use higher level languages, and higher level languages are exactly what they say. We can do a lot of operations by saying, move data from here to here, or add some things together, or multiply. And the multiply might actually be tens or hundreds of instructions inside the computer, but we only have to say multiply. So what we do when we write a computer program is we write in a higher level language. We're going to write in something that it's in an environment that's called Arduino, but the reality is it's a programming language called C with some modifications. It's somewhat simplified. We're going to be able to read those instructions because they're human language. Not quite, but they're fairly easy to read. Now, when you write code, you can make it easy or hard to understand. You can say output to pin 5. Every so often we want to turn a pin on or off. That's an external pin on the microcontroller. That's not very clear. Or we can say output to the red LED pin. Obviously, if you're reading the code, outputting to the red LED pin is a lot clearer. You get to choose how clear you want to make your code. My advice is, from the beginning, start writing code that's clear and understandable. Two reasons. One is, most of the time I'm grading it, I have to understand it. And in real life, what looks like very clear code to you will not look very intelligible about a week later, much less a year later. All right, so we write this code, we write it with a text editor, we can write it in the Arduino environment. We then compile it. Compiling is the process by which a computer program, in our case running on our PC, reads our sort of human language programming instructions and converts it into the ones and zeros, the binary that the microcontroller we're using understands. We then download that through a USB cable into the microcontroller we're using. At that point, the microcontroller resets and starts executing those instructions. We can reset it also by pressing a button on the microcontroller board. We always start with the first instruction at location 0 in memory, and we just execute those sequentially unless there's something in the program that says go somewhere else. All right, let's take a look at Arduino programming. And that means I'm going to go share some screen again. All right, so this is a good place to go. This is the Arduino language reference. This is the commands that we can make, and there's different kinds of commands. There are functions. Functions are little programs that do things that have already been built into the language. For example, if you want to take the cosine of a value, you could write a cosine routine. As you know, that there is a bunch of ways you can do that. You can use lookup tables. You can use infinite series, which you truncate. There are approximations. You don't have to worry about that because somebody else has done it for you. And functions in Arduino consist of a function name. In this case, the function is called cosine, C-O-S, and parentheses. Parentheses are the thing that lets the compiler know it's a function. And also, if there's an argument, that's a value you give to the function because it needs an argument. For example, cosine needs to know what angle you want the cosine of. You would put it inside the parentheses. So you'd say cosine 0 to get the cosine of 0, which is 1. And when you execute that instruction, it would return a value, in this case 1. You'd have to use that value in your code. So your code would call cosine 0, cosine parentheses angle, and it would get back a value that it could use. So these are all the built-in functions that are in our Arduino. And you notice they're sort of divided up by what they do. There's some that do I/O, which is input-output, that writes to a pin or reads from a pin. There's some that can do analog I/O. There's certain pins that can take in an analog voltage and then turn it into a digital number between 0 and 1023. Those use internal analog to digital values. So a value of 0 volts on the pin gives you a value of binary value of 0. A value of 5 volts on the pin gives you a digital value of 1023. We've got a bunch of things that allow us to do characters, so we can write letters to the screen. Let's see, we got some stuff that allows us to do time. In order to operate on data in a microcontroller or any computer, we have to use binary values that are stored in data memory. And those binary values can be represented, as binary values, as hex values, as floating point values. And we use a concept called variables in PCs. And what that does is it allows us to allow a human readable name to data. So I can create a variable, and by variable I mean something that can change its value, named sum, S-U-M, and then I can say what kind of type it is. It could be Boolean, it could be 8 bits, it could be a floating point value, it could be an integer. integer could be 16 bits, it could be 32 bits. Unfortunately, it's dependent upon the particular microcontroller you're using. For the most part, we don't care. The only time you care is if it's only 16 bits, that only allows you to go plus 32,000 to minus 32,000. Whereas if it's 64 bits, you can go much further. As long as our numbers are smaller than 32,000, you don't have to worry about it. And there's a whole bunch of other types. Long just happens to be an integer that's guaranteed to be at least 32 bits. Short is an integer that's only 8 bits. You're not going to have to worry about this. I guarantee that mostly if you use integer, float, and occasionally byte, and Boolean, bool and Boolean are both the same as far as I know. If we click on this, it's a non-standard alias for Boolean. That means that I think I actually use Boolean but bool happens to be a value that only knows 2 values, true and false. All right, so we have all these data types. You only need to know a few of them. You can have, they are assumed to be 2's complement, which is to say they can either be positive or negative unless you prefix them with the keyword unsigned. Unsigned means that the integer, instead of going from plus minus 32,000, if it's a 16-bit integer, goes from 0 to 64,000. Once again, you're not going to have to worry about that much. There's only one case where you're going to need to. There are some functions that convert between different values. You have to be a little careful in the Arduino. If you try and use an integer as a byte, which is to say you've got this 16-bit binary value, but you're using it as an 8-bit value, you won't be told that isn't a good thing to do. It will just somehow make that integer into an 8-bit value. That may work fine, it may not. A lot of languages are strongly typed, and they will complain if you try to use an integer where the function expects a character. And that's to keep you out of trouble, because they don't want to make an assumption about what you meant. To make Arduino easy, it essentially does type conversions for you. You don't have to worry about it, but you can get in trouble. Now, we also have a bunch of operators. You know, we can do various arithmetic operations, multiply, addition, subtraction, division. We can assign a value to a variable. There's a remainder operation, 5 remainder 2 is 1, because if you divide by 5 by 2, you get 2 with 1 left over. There's a bunch of comparison operators, less than, greater than, equal to, not equal to. You can do Boolean operations. You can logically not. So if you have a value that's true and you take the not of it, you get a false. You can logically and. So true and true is true, but any other combination is false. Or same thing. Or and or is false and false. False or for false is false, but false or any true value or true is always true. These are just or and not and gates, but in software. There's a bunch of other operators. Most of them we don't have to worry about. There is control structures, which we'll talk about sort of at the end, which allow us to make decisions based on values of data. So the structure of, yeah, go ahead.
So like those 3 operators you just told us are like gates. Are there like NAND gates, quote unquote, or would you have to use like a?
No, there's not NAND gates. If you really needed a NAND, you could do an AND and a NOT. But it turns out that in software, you rarely have to do that. In software, you know, you don't have the limitation of active low signals. So typically, you just invert a signal if you need to invert it. If you really need a NAND, you'd take the logical AND of 2 things and then take the inversion of it. You put parentheses around things to force them to happen first, precedence. There's a natural precedence. It's just like if you see 3 plus 2 times 5, what gets done first? Well, if you're human, you have to decide what gets done first. If you're a computer, it's going to do something first. It's either going to do left to right, or it's going to say multiplication is more important than addition. Don't worry about it. Just put parentheses around the things you want done first. It is a dangerous thing to rely on precedence because you have to remember what it is. I don't do it. I always put parentheses around things to make sure I know exactly what's happening first. All right, where was I? Okay, so let's talk about a basic Arduino program. So the reason Arduino is so successful is it takes using something like this microcontroller here. This, by the way, is very similar to the one we use. It's an earlier version that we used to use in ES52. So this microcontroller right here is a complete computer. It's got the computer part called the CPU, but it's also got memory, both data memory and program memory. It's got a clock inside it that runs the finite state machine. It has input, output. It actually has a whole bunch of peripherals. Peripherals are things that allow you to talk to external devices. For example, there is a standard that allows you to talk to computers called the UART, which we'll talk about later in the course, and it requires a piece of hardware called a UART. RS-232 is the standard, and that's built in. So there's a lot of stuff in here. It does everything you need. Oftentimes when it starts up, there's a lot of setup that needs to be done. That's all done for you when you use Arduino. And in fact, what Arduino does is, where's my Arduino Pro code? Okay, so let's open the world's simplest Arduino code called bare minimum. So this is a bare minimum. This is the Arduino environment that runs on the PC. This is the world's smallest Arduino code. Every Arduino program will consist of two functions, one called setup and one called loop. Now, this word void in front of setup says that setup does not return a value. When you look at a function, particularly if you build your own, so there's a bunch of setup built-in functions, they all will either return a value or not. And when you look at the documentation for them, let's go look at something. In fact, let's go look at cosine because we were looking at that before. So if we go and look at the definition of cosine, cosine, where does it say? So cosine takes a value, and it's the angle in radians, and it returns the cosine of the angle, and the type is double. Double is a floating point value that has higher precision than a normal float, and radian is a floating point value. So normally we'd call cosine with something like cosine 3.1415, which would give us the answer 1 because the cosine of 0 and 3.1415 radians is 1. And 3.1415 is a floating point value, and you know that because it's got a decimal point in it. 0 could be a floating point value, or it could be an integer value, and it will work fine because this will not complain. It will not say, hey, you gave me an integer value and I was expecting a floating point value. Normally, this is not good documentation because it really doesn't show you much. The correct way you would normally see that is up here. Everybody can see the code void setup parentheses. This tells you two things. It tells you setup takes no parameters or arguments. That's because there's nothing in the parentheses. This defines the setup function, and void tells you it doesn't return anything. If void was instead int, it would say the setup function returns an integer. Okay, so this says we're defining a function called setup, doesn't take any arguments, doesn't return anything. This function is called once whenever you reset your microcontroller. Okay, what good is that? Well, normally there's a bunch of things you have to do once. You need to define your variables and initialize them. You may want to set up your pins to be either input or output in order to maintain maximum flexibility. Any pin on any input-output pin on the Arduino can be either an input or output, but you have to tell the program whether you're going to use it as an input or output, and there is a function call that does that. There's a bunch of other stuff you might want to do once. After setup is called, and this is all being done by the Arduino environment that's been loaded onto your microcontroller, the Arduino environment calls another function called loop that you have to write, and that's already here. So here we're defining another function called loop. It doesn't take any arguments. It doesn't return anything, and it executes, and you do whatever your program is supposed to do in loop. and then loop gets called again, and then loop gets called again, and in fact, loop gets called forever. So you should plan your program, whatever you want it to do, to set up everything that needs to be set up and set up, and then loop just keeps executing over and over again. And we'll see how that works. So,
Question?
yeah.
So you would write, so when you're like setting up, are you like defining your variables and loop is like where you do your functions?
Typically, you define your variables before setup. In setup, you might initialize your variables or set other things up, like say you're using some external stuff that you'd like to turn on or turn off before you get started. We'll see as we go along the kinds of things you do in setup, but you do stuff in setup that only needs to be done once. In loop, you just do whatever your program does. You know, if it waits for somebody to open the door and then turns on the light, loop sits there saying, is the door open? No. Is the door open? No. Is the door open? No. Oh, the door's open. Turn on the light, right? And in fact, it might want to say, is the door closed? And if you say yes, it might turn off the light, but it just does that forever. Now, what does setup do? Well, setup might start with the light off, or it might, you know, do nothing. You don't have to use setup. Setup can be empty. You don't even actually have to use loop if you don't want to. But for the most part, the structure of an Arduino program is a bunch of setup stuff that you do once, and then you loop forever. It makes it super easy to write code. Now, what does code consist of? So we can take this and let's start by saying, we're going to define a variable. In this case, I need that variable to be an integer. So I say int. By the way, when you see it in light blue like that, that means it's a keyword. It's a special word that's part of the Arduino language. If I did integer, it's black. That means if I think I'm using a keyword and it's black, it means I made a mistake. So the first hint, int, that says I'm going to define a variable called int, and I'm going to call this LED pin. What does that mean? Well, I can call the variable anything I want. It has to be a single word, which is to say I can't have spaces in it. Arduino is case sensitive. LED underbar pin capitalized is a different thing than LED pin in lowercase. If you write your variable in uppercase one place and you write it in lowercase somewhere else, when you try to compile it, you'll get a complaint that it doesn't know what one of them is. In general, there are conventions where you use uppercase and lowercase, and in particular, I'm pretty insistent that if something is a constant, if the program never changes it, I write it in uppercase because it tells me that it never changes, and that's useful information. Okay, so LED pin is the pin on this circuit board down here. Where did my IP? The pin that is connected to this LED right here. There's an output pin that's connected to the LED. If the output pin is high, the LED is on. If the output pin is low, the LED is off. It could be the other way around. I don't know for sure because I'd have to look at the documentation. It doesn't actually make too much difference, but we can find out by testing it. All right, that happens to be pin 17. So this is a statement in Arduino code. It uses the correct Arduino sequence to do something, in this case, define a variable, and it ends with a semicolon. All Arduino statements end with a semicolon. Now that would be really easy, except there's also something called directives which do not. So when I get to directives, I'll talk about it. But in general, everything ends with a semicolon. If you don't put in a semicolon, weird things happen, because what happens is Arduino just assumes that you haven't finished what you're doing. And even if you do something on the next line, it assumes it's part of the same statement. So make sure you end with a semicolon. If you want to add a comment to remind yourself what you're doing, double slashes and anything after it, this is ignored. Whoops, I can't spell. So this is ignored. I can put anything I want there. All right, so now I've defined a variable, and I've set that variable to the value 17. I need to do it with an equal sign. So equals is the assignment operator. So I have created a variable, I've given it a name, I've given it a value. Now, I don't actually have to create a variable for this. I'm going to use a statement, a function called digital output that outputs either true or false to a pin on the Arduino. And I could use the value 17 in that function. The problem is somebody who's unfamiliar with this board and sees a digital output setting pin 17 to true or 17 to false isn't going to know what it's doing. But if they see that it's called LED pin, then it's kind of clear what it does. All right. Let's go on a bit more. So we want to group statements together. For example, we've defined this function setup, and we're going to have several statements potentially in setup. How do we tell void setup, which is the function, how many statements there are in it? We put them in brackets. So these are curly brackets. And what this says is everything between the beginning left bracket and the ending bracket is part of this function setup. So if I want to do something like, oh, let's do a digital write. That's the function that writes a true or false to an output pin. This is going to have to end with a colon. And the syntax for this, once again, you look this up, is the pin that we want to use. In this case, it's LED pin. And the value. And I'm going to set it. I can use true or false, or I can use low and high. Since this makes much more sense, low and high, I'm going to go ahead and do that. By the way, one thing I do not like about Arduino is there are built-in constants. True and false, high and low are built-in constants. Notice when I put low, it's in light blue. And if I put false, it's in light blue. Those are both constants. All the built-in constants are uppercase, except for true and false. I have no idea why that is. It annoys me. I like my constants to be uppercase. So I'm going to use low. So what this does is say, let's start out with the LED pin low. Suppose I had some other statements I needed here. I could just add them, and as long as they're inside the curly brackets, they would be executed whenever I called the function setup. If I didn't have the curly brackets, setup would only execute the first statement, and the rest would not be executed. This is important because we're going to get to other code where if you only have one statement, you don't need to use curly brackets to group them together. But my advice is always use curly brackets where you have something where multiple statements could be used. And here's the reason. You will say, oh, I only have one statement. I don't feel like typing the curly brackets. Sometimes later you'll realize you need another statement. You'll go back and type that other statement and your code won't work right because you forgot the curly brackets. So as you'll see later, we always add the curly brackets. Now, parentheses and curly brackets always have to be balanced. So if I put the cursor near this parentheses, it shows me the other matching one. If I put this near this brace, it shows me the other matching one. There has to be an equal number of left parens and right parens, or left braces and right braces. If you don't do that, you will get errors. The compiler's job is to see if there's syntax errors. Syntax errors are mismatched braces. Unfortunately, while it will tell you there's an error, so it's not terribly good at telling you where it is. All right. I already said things are case sensitive. Everything's case sensitive. Setup, all lowercase, would be a different function than capital S, ETUP. So that's something to be very careful about. Digital write is a lowercase digital and write capitalized. If I wrote this, notice it's in black. That's a hint that I made a mistake. If I do it correctly, it turns orangish red. That tells you that it's a built-in function. So blue tells you it's a keyword or a constant. Reddish rust color tells you it's an internal function. So keep an eye on that. The editor will give you some hints. The fact that this is a lowercase first word and an uppercase second word is a convention. It's not required. Functions can be just lowercase if we want. Loop and setup are lowercase. In general, we have some conventions. Variable names normally start with a capital letter. unless they're constants, in which case they're all capitals. And function names normally if they start with a lowercase, but if there's multiple words in them, every word after the first one has a first letter capitalized. Those are standard conventions. You don't have to follow them, but the value of them is when you look at something, like if I look at this, I know it's not going to change. It is a variable, so if I wanted to give it a new value, well, I could, but that's a bad idea because I've said it's not supposed to. In fact, there's even a keyword, constant, C-O-N-S-T, and what that does is that tells the compiler, I don't expect that variable to change. Hopefully, if something in my code changes that variable, I will get a warning about it. Using const is optional, but it's a good idea. Anything you can do to have your code help you out is not a bad idea. All right. Comments. Comments are a really good idea. Here's the thing. When you write your code, it is crystal clear what you're doing. Why? Well, you're thinking about it. It is amazing how fast you can forget what you were doing. You will see me comment all the time. There are two ways you can do comments. This kind of comment, the double slash, everything is ignored until the end of the line. Notice, by the way, it's in gray. Gray means the compiler is going to ignore it. There's another kind of comment, which is a block comment, and that consists of a starting slash and an asterisk. Everything after that until the next asterisk slash is ignored. So if I wanted to do a multi-line comment, I would use that. Now notice that I can come out my entire code if I'm not careful. Because like curly braces, there always has to be a starting slash asterisk and an ending slash asterisk. And one of the things that the editor will do is if you type a slash asterisk and hit return, it will put in the ending for you. So now I can say, I can write as much stuff as I want to. And typically, at the least, you should always have a program header at the top that tells what the name of this thing is. So that's a block comment. I strongly urge you to use comments in your code. It will make your life much easier when you try to figure out what you're doing. You also tend to use a block comment when you define new functions because you want to explain what your function does. You don't want somebody to have to read the code to figure out what a function does. So that's comments, both block comments and short comments. All right. Variable names. So I want to define a floating point variable, and I'm going to call it y. Well, that's perfectly legal. I've now declared a variable called y that can be, you know, a floating point value, which means it can be pretty big because it has both an exponent and mantissa. That's not a very useful value unless y was a y-axis value. It might be better to do that's a much more useful name. So there's no reason, and we have a convention that we normally have a capitalized first. We use something called camel case, which is every word is capitalized. So when you name variables, try to name them something that helps tell you what it is. Float temperature is much better than float y if the value is the current temperature. And it wouldn't be a bad idea to say, because who knows whether it's F or C. You can use, I mean, there are places where, for example, I, J, K are often used as just, when you need a very fast variable that just counts from 1 to 10 or something, I, J, and K are traditionally used. By the way, notice I can declare multiple variables on a line by separating by commas. So you'll see me declare int I or int j all over the place because I have a count that I'm counting, and I just need a variable to count, and it doesn't make a difference what it is. And I sort of know if it's I, it's just an integer variable that I'm counting with. But if you've got a variable that means something, it's a good idea to give it a useful name. Variables always have a type, float, int, the other one, Boolean, and you know, that might be a good name for a Boolean. I know that if it's true, the LED is on. The assignment is optional when you declare a variable. On the other hand, you can get in trouble by having a variable that you declare, but you don't say what its value is. Because if you do that, its value is whatever the computer decided that be when you reset it. If you use it before you set it to a variable value, it can do bad things. So in general, it's not a bad idea to initialize your variables when you declare them. You know, maybe I want to set my temperature. Why would I pick that? Well, I know that if suddenly I'm displaying minus 100, that's not a real temperature. I made a mistake. I intended this to be, by the way, I should use a period to tell it, to say this value is a floating point value. This value, without a period, is an integer, minus 100. The compiler will convert it to a floating point value, but it's a good idea for me to just say use a floating point value. I picked minus 100 because that means that if I see minus 100 anywhere, I probably made a mistake. I didn't intend to use that value. But initializing a variable is optional. Every variable has a type and a value. Whether you initialize it or not, it has a value. It can't have no value. It's just if you don't initialize it, you don't know what the value is. You must declare variables. This is called variable declaration up here before you use them. If I declared, say, temperature down here, but I used it up here, the compiler would give an error because the compiler is really stupid. It only goes through the program from beginning to end. And if it gets to the word temperature, but it doesn't know what it means, it will whine. You can declare variables either outside any function, the way I have here. And if you do that, they're known as global variables. That means any function can use them. If you declare a function if you declare a variable in a function, it's local. Only that function knows about that variable. So if I declared this variable in setup, I could use it in setup. But if I tried to use it in loop, I would get an error. This is not something you have to worry about a whole lot. In general, what you will find is we are going to use mostly global variables. Global variables are actually a bad idea. And the reason is, if you want to use the same variable for a different thing, it can be confusing. But for simple programming in Arduino, we normally declare our variables right at the beginning of the program.
And these variables in the function, when they're inside the function, they're inside those squiggly brackets?
Yeah, anything inside the curly braces is the function. When you say setup, if this program somewhere had setup with 2 parentheses in it, what would happen is the code inside this function declaration would get executed. It would be just the same. So if down here, you would never do that. I hate doing something that's a bad idea. So let's create a function that doesn't return anything. Well, let's create a function function called int return 1. So it doesn't take any parameters. By the way, when I type left curly brace and hit return, the editor automatically puts the response. And what do I want this function to do? I want it to return the value 1. It's a really boring function. Return is a keyword. And what it does is it comes back from the function with the value you tell it. In this case, I'm saying return the value 1. All right, so down here, I say, gee, I've got an integer I, so I say I equals. So this is a function call. How do I call a function? I just use the function name. So what happens here, I come down here, I execute digital write LED pin low, so pin 17 gets set to 0. I then execute the return 1 function, which means whatever is in the curly braces here gets executed. It's exactly the same as if I copied everything that was in the curly brace and put it over here. And then whatever value is returned by this is assigned to the variable I. And the result is I equals the number 1. Does it make sense? All right. Constants. We can define our own constants, or we can use the ones that are built in. The ones that are built in are listed here. Whoops. Previous page. Down here. Where are our constants? Here we go. Okay, so high and low, true and false. Notice true and false are lowercase. I don't know why. There's input, output, and input pull-up. You'll see what we do with those in just a second. They're important. LED built-in means the pin that the built-in LED is on, because on different Arduino boards, it's connected to a different pin. On this board, it's connected to pin 17. On the Arduino Micro that you have, it's connected to pin 13. I'm doing something where I'm using because I'm using this board as though it were an Arduino Micro, I have to tell it explicitly what pin it's on. But if you use LED pin built in, you don't have to figure out what pin it's on. There's also some integer constants, which explains how you define integer constants. We will get to that in a bit. So really, there's not that many: high, low, input, output, input, pull up, and LED built in. Now, I don't think we've gotten there yet. Let's see, what are we up to? All right, that's fine. There are something called directives, and you know it's a directive because it starts with a hash sign. So a hash sign is a directive. A directive means it's not part of the language. A directive is to the compiler. It tells the compiler to do something. There's really only one directive we really care about. That's a directive called include. Notice, by the way, that it went from black to gray. Anytime you see the color change from black, that means it's something built into the Arduino environment. And include takes an argument that's in left-right pointy braces, and that's the name of another file. It's a file on your computer. Some of those are there, but you don't even know it. For example, the one we are going to, I don't think we're going to use because I didn't send you home with the accelerometer, is called wire.h. H stands for a header file, and header just means it's a bunch of statements that often are used by other programs, often enough that rather than type them into the other program, we're just going to put them in their own file. And include essentially reads all the text that's in the file called wire.h and sticks it right where you see it now. So it might be a bunch of constants. For example, instead of doing constant int LED pin equals 17, we could put it in another file and call it .h. You don't have to call it .h, but it's a good idea because people know what header files are. And then if we include the name of that file using the include directive, it would be read in as though we had typed constant int LED pin equals 17 colon. The reason this is used is there's a lot of libraries included with the Arduino environment. Libraries are new functions that aren't part of the cosine, for example, is part of the Arduino environment, but arc cosine isn't. I don't think we saw arc cosine there in our functions. No, we only got cosine, sine, and tangent. Well, suppose you needed arc or arc sine or arc tangent. It's possible that somebody has written a library, and the library has those functions in it. And in many times, those libraries are just available built into the Arduino environment. The include file, in this case, is for a library called wire. The wire library lets you talk to peripherals using various protocols that are hard to write yourself, but are available not as part of the Arduino itself, but as part of a separate library. Now, the distinction is really not very important to you, except that to use a function that's built in, like digital write, you don't have to do anything. To use a function that's in the wire library, you have to include its header function. How do you know about libraries? Well, it's all part of the documentation. Here's the Arduino reference. Where, let's see, somewhere in here we have to figure out where the libraries are.
Cartoons?
Yep.
If you have a library with like, and like it opens up the text file and like it has all those functions are defined in the rest of the code. So like I could use those functions like later.
Yeah, once you've included a library, for example, here are some libraries. Notice there's some called these standard libraries. That means that they are available in all Arduino environments, and they do things like, you know, running stepper motors, running servos. For example, the hobby servo that we ran by building our own hardware that changed the duty cycle. There's actually a library that does that, where you just say the angle you want the hobby servo to be and what pin it's connected to, and it does it for you. And if we click on the servo library, notice it's got these functions. We have an attach, write, read, attached, and detach. Before we use it, we do but in order to use it, we have to include servo.h. And once we include servo.h, these are essentially built-in functions. We have to start by attaching our servo. My guess is we have to tell it what pin we want to use. Then we can write to the servo the angle, and then we can detach it when we don't need it anymore. And then there's some other stuff too. If you want to know what angle it's at, you can read it. If you want to find out if it's attached, you can. But this library is not part of Arduino, but by including its header file, it's as though it were part. So I don't want to belabor the point, but we use the include directive. And the important thing is directives do not have semicolons on them. So if you see a hash mark, it's a directive, no semicolon. It's a little confusing because everything else gets a semicolon. All right. Math and computation. So the simplest math we do is assignment. Int, let's call it test variable. So I've just set test variable. I've created a variable. This variable is only valid within this function, and I've set its value to 6. I could set it to 8. I could set it to 128 divided by 8 if I wanted to. That's, by the way, 16. You can do, the compiler actually calculates what this value is. In fact, you know, you can do fancy stuff. That works too. Why would I want to do that? You might do that because it's clearer in a particular application. But you probably want a comment to explain it. But the point is, this equal sign here is an assignment variable. Whenever there's a variable on the left, it assigned to whatever the value of the thing on the right. By the way, the thing on the right can be another variable. In this case, it happens to be the constant LED pin. This statement sets a test variable to whatever LED pin is, which in this case is 17. So you can assign a variable to a lot of things, or you can assign it to a function. Let's see, what would be a good function? I'm trying to think of a function that returns an integer offhand. So analog read reads the analog value at pin 2 and converts it into a value between 0 and 123. So I'm setting test variable to whatever this function returns. By the way, if the function or if the assignment is not an integer, the program will automatically convert it to an integer without telling you. That may be what you want, but it may not be. So just be aware of it. We can add variables. We can say that test variable equals, let's go up here. I'm going to set.
Sorry, what does analog read do again?
I'm sorry?
What does analog read do again?
It reads a pin on the microcontroller and converts the voltage at it to a value between 0 and 123 for a voltage between, a value between 0 and 1023, but for a voltage value of 0 to 5 volts. It's an analog pin. All right, so I've set ints I, j, and k to 3 different values. I can do math and say test variable equals I plus j. All right, well, that just sets test variable to the number 1 because I equals 0 and j equals 1. I can also do something that's a little strange. I can say I equals I plus j. Well, the thing on the right gets evaluated first, and then I get sent to that value. So this function, let's change this function now. This function returns I, so let's call this return function called increment and return I. So I'm calling this function increment and return I. It adds j to I, sets I to that value, and then returns the value of I. Well, I starts out as 0, j is equal to 1. When I call it the first time, it adds 0 to 1, sets I to 1, and returns I, which is 1. The next time I call it, I is now 1, j is still 1. It adds them together, gets 2. So I get set to 2, and then it returns 2. And as long as I don't change j from the value 1, every time I call it, it increments I by 1 and returns I. So you can actually assign a variable to a value that's calculated on itself. There's nothing wrong with that because it uses the current value to evaluate the right side of the assignment. Now, what does that do? I don't know. If you wanted to read the precedence rules to find out if it evaluated this equation from left to right, which case it would add I and j and multiply it by k, or if multiplication has higher precedence than k, which is what I suspect, that's fine if you want to memorize the precedence. The problem is when you go back to read this code later, you might not know what it does. I always use parentheses. If I know that what I'm really counting on is multiplication has higher precedence than addition, I don't care. I'm going to put parentheses around it, and that way I look at it. And I know instantly that j gets multiplied by k before it gets added to I. Use parentheses liberally. They don't cost anything. All right. How can we increment a variable? Let's just call this increment I. This is a stupid function, but it's not going to return anything. And I need to increment I. How can I increment I? There's a lot of ways to increment I. One is I just set this to I plus 1. That increments I, obviously. It takes the value of I, adds 1, and increments it. I can take and use a shorthand. Whoops, sorry about that. Suppose I want to increment I can use a shorthand, which you don't have to worry about because you should use I plus 1. But if you ever see plus equals, multiply equals, minus equals, what that means is I plus 1, I times 1, I minus 1. This is a C shorthand that people like to use. Just be aware that's what it means. There's another way to do it. That increments I by 1. That also increments I by 1. They're actually subtly different. I don't want you to worry about it. Please use the first one. The only time the subtle difference makes a difference is if you're using it within an equation. If I say let's say I do I equals 1. So I've set I equals 1, and I say print this. Right. That prints I plus 2, which is 3, and then it increments I, and I becomes 2. If I do this, since the plus becomes before the I, this increments I to 2, adds it to 2, and prints 4. That's a very subtle difference. I do not expect you to worry about it. I would expect you to use this. And this is actually used quite often. When you're in a loop, you have an increment variable, iteration variable that you have to increment. And I++ is a lot easier than writing I equals I plus 1. So you will see this fairly often. Other mathematical operators: plus, minus, multiply is an asterisk, divide is a slash. Be careful when you're dividing integers. 5 divided by 2 is 2. 4 divided by 2 is 2. 3 divided by 2 is 1. You get an integer result. It throws away the non-integer part. It doesn't round. There are functions to round. All right. We have some Boolean operators.
If you wanted to do, if you wanted to get like the actual answer, you'd do float.
Yeah, you do float if you need actual answers. The Boolean operators, we have an invert. So if I have a Boolean, did I create a Boolean? I got LED up there. So if I say LED on equals not LED on, if LED on was true, this sets it to false. And if it was false, it sets it to true. So the not operator inverts the true false value of this variable. By the way, a variable is false if its value is 0. It is true if it's anything else. That means even integers and floats can be used as true false variables. But if an integer is 5, it's true. If it's 32, it's true. If it's 500, it's true. It's only false if it's 0. If you invert it, it will go to 0 if it's true. If you invert it again, my guess is it goes to 1, but I don't know what that is what happens or not. Okay. You also have the function and. If I say LED on and I need another variable. Let's open. That result will be true or false. It will be true if the LED on is true and the door open is true. It will be false any other time. Or says that output will be false if LED on is false and door open is false. Otherwise, it will be, if either of them are true, the output will be true. So it's just an AND gate and OR gate. By the way, make sure you don't use that or that. Those actually those are bitwise operations. They do first bit compared to the first bit, second bit compared to the second bit. They do something very, very different. These always have two ands or two vertical lines. Those are your Boolean operators. And then finally, there's the built-in math functions: sine, cosine, tangent. Those take floating point values. They return doubles. Doubles have more precision than floating point. And that's because, you know, you get the sine of very small angles can have very long values. All right. Functions. We did a function up here. Functions are either built in, part of a library, or you write them. You normally want to use functions. When you write loop, you would like it to be fairly short. You don't want a lot of code in there because it's hard to understand. Once you get more than a page of code, it can be pretty hard to understand because you have to scroll through it. You have to figure out what's going on. So normally what we do is we write functions that do part of what we need to do. For example, if we wanted to know if a door was open or not, instead of just checking it in loop, we might call a function that says check door open, and it returns true or false. True means the door's open, false means it's false. And maybe it takes a bunch of stuff to check if the door's open or not. But if we see that function in loop, we know what it does. What we've essentially done is we've moved the complexity of that operation somewhere else. The other reason we can move things into functions is, what if our hardware changes? What if the way we check that the door open changes? Well, that's not really important. If we want to check if the door opens, we want to turn on the lights, we want to do stuff, we don't care how we check if the door opens. We just want to know if it's open or closed. By moving into function, we isolate the complexity of checking if the door's open with the actual thing we want, which is the door open or not? So use functions to isolate hardware in particular, which might change, but also just to make your code more readable. One of the functions that we need to use, and we have not, so this code would not have worked, is we have to say whether a pin on the Arduino is being used for input or output. So we need to set pin mode. This is a built-in function. Because when you start up, pins are, I think they're set to input, but I wouldn't count on it. So we have to say, let's set the LED pin. So we say which pin it is. You could use a number. You could use 17, but that's not very helpful to somebody reading this. Let's set the LED pin. And our choices are input, output, and input underbar pull-up. Why pull-up? Well, we know that if we're using a push button, we have to connect one end to ground, but the other end has to be connected to pull-up resistor, or it's floating. Turns out there are pull-up resistors inside the Arduino, so you don't have to use pull-up resistors externally. You just have to say input pull-up. But this is actually an output pin, so let's set it to output. So now we can use the digital write function. We can't use the digital write function until we've said this is an output. Since I've gotten rid of this. So now there's my setup. My setup sets the pin as an input or output, in this case an output. And now it says I'm going to set it low. All right. Built-in functions. Your setup will almost always have a bunch of set pin modes because we're using a microcontroller. We're using it to do things external to the microcontroller. Every pin you use needs to be set up as input, output, or output pull-up. And normally, input, output, or input pull-up. So you're going to set the pin to one of those values, and you're going to do it in setup because you only have to do it once. You also sometimes do other things in initialization. Oftentimes, you'll assign variables if you have not assigned them values up there. Sometimes you'll set external hardware to a known state. Like, you might want the LED to start up off. So that might be what low does. I'm assuming this pin's active low, but I'm not positive. We can see, hang on, I'm going to run this code. Now, when I say run this code, down here it says it's compiling the sketch. Notice it complained. It said, fatal error, wire H, no such directory or file. So it could not find wire.h. That's probably because I don't have it set up to do that. I don't really need it, so I'm going to get rid of it. If you don't want to download the code, if you don't have your computer, your microcontroller hooked up, you can just compile the code with the check mark and make sure it compiles with no errors. Until it compiles with no errors, you don't have a working function. Now, it's compiling. It says set pin mode is incorrect. Set pin mode was not declared in this scope. So I've made a mistake. Well, no problem. I just need to go to the library, the reference. And this is an IO function. So I need to find my IO. And it's not set pin mode. It's just pin mode. All right, no problem. I can go back and change my code. Compile it again. Pin mode was not declared. Why is it unhappy? It's lowercase p. That's what I mean about case sensitive. You will be very confused unless you realize that it's case sensitive. All right? Oh, it's happy. All I got was white. So now I can compile it and download it to my microcontroller. compiling and uploading. And let's see what it does. The LED is on. So that means that this LED is active low. So I need to, if I want it to start off, I need to set it high. I could have looked at the schematic to figure that out, but it was just as easy to write some code. So now I download this and set it low. All right. If we want to know, suppose we want to set the Boolean value, the LED on equals, we want to know whether the LED is on or not. Well, we can do a digital read of the LED pin. So that will read the LED pin, return either true or false, and set the variable LED on to either true or false. That's pretty good because LED on is a Boolean value. The problem is digital read is going to give us a 1, but we know that the LED is on when the pin is 0. How can we fix that? Well, there's two ways we can fix it. We could say LED on equals not LED on. So we just say we read it, but then we set it to the other value. That works fine. We can also just say, well, call the function digital read and then give us the opposite value. So this not says do digital read, that returns true or false, and then set LED to the opposite value. So that's an assignment. All right, let's see, that was 3, 4. Control functions. Yeah, let's do control functions. So now we know how to write code. We can assign things. We can do calculations. But what if we want? Go ahead.
Why do we write, like, why can we just write pin mode and digital write for like those type of functions, but for other functions we have to like do like squiggly brackets?
Well, we use squiggly brackets to define a function.
Okay.
This is a function definition. This code right here does not execute unless it is called. This is a definition. It turns out it is called, and it's called by the thing that is the Arduino environment. But this is not, this code doesn't get executed until the function setup is called by something that does somewhere, not in anything you have to write, there is this line of code. And that line of code calls this function. So braces, this is a definition. This is how you create a function. This is how you call a function. You call a function with its name and parentheses. That's the difference. Now, so now we're in pretty good shape, but now we want to make decisions. To make decisions, we have to a way to alter a structure. This function, loop, calls LED pin and sets LED on to whether that pin is high or low. It does that forever. Suppose we wanted to set the LED to the opposite state. If it was on, say that if the LED is on, we want to set it off. Well, we use a function, an if statement. So if is a keyword. You put the arguments for the if in a parentheses. In this case, if does a comparison. So if LED on is true, so this is a comparison. Notice there's two equal sign here. This is really important. One equal sign is a comparison. This sets LED on to true. No matter what it is, it will set LED on to true. The if statement will then execute because the if statement executes if whatever's in the parentheses is true. Two equal sign says compare LED on with true, and if it is true, do what's in the curly braces. Now we put some statements in curly braces. Well, if the LED on is true, let's set digital write LED, whoops, LED pin, comma, high. All right, so if the LED is on, we're going to set the pin high, and it turns out high is off because it's active low. All right. The only time we will execute the statements in these braces is if the value of this variable equals the value of that constant. If the LED is already off, we do not execute anything in braces. So that's a conditional statement. You can also, I'm sorry?
Does the indentation matter?
No,
Like
indentation does not matter. I could write this like this if I wanted. I will be annoyed with you if you do. That's a legal statement. These statements only get executed if LED on is true. This is also perfectly legal. White space gets ignored. This is also perfectly okay. You can do whatever you want. Don't annoy me by making your code hard to read. This is not easy to read. So if you're going to do something, my standard way of doing it, oops, my keyboard has been acting up. Hang on. See if I can get my keyboard to stop. Ah! Need a new keyboard. This is bad. Okay. My standard way of doing things is to indent every level of curly brace. And that's actually standard in most C. You know, this brace lines up with the thing that is the starting brace. In this case, that if. And if I had another if in here, this is, by the way, a legal statement. It's never going to execute. I would write it like this. My ending curly brace always lines up with the thing that started it. I indent everything that's within curly braces. This statement says if 5 is greater than 8, do this stuff. Obviously, 5 is never greater than 8. But I could say if I is greater than 8, execute this. So I can do greater than, less than. I can do greater than or equal to if I want. I can do not equal. You should look up the comparisons, but there's lots of comparisons. The comparison is made. If it's true, it does it. By the way, I can also have an else statement. Else. So if I is greater than 8, do that. Otherwise, set I equal to 9. That's perfectly okay. If this is true, these statements get executed. Otherwise, these statements get executed. So you can do something or something else. That's a useful control structure. Another control structure we will use quite often is the for structure. It's used for iteration. So I always start like this because that's my structure. The for structure has 3 parts in it. I have to have an iteration variable. In this case, I need, and that variable has to be defined somewhere. Usually it's one of the ones at the beginning. You can, if you want, declare it right here. That's perfectly acceptable. So I've declared a variable x. It's an integer. It's only used within this for. Use semicolons to separate the 3 pieces. So you start by declaring your variable and setting it equal to your starting value. You then say your ending value. As long as x is less than 10, I'm going to do whatever's in the curly braces. And after each time I do something in the curly braces, I'm going to increment x by 1. You don't have to do that. You can start x at any value. You can have any ending condition. And you can do anything you want to x every time you do an iteration. But I will warn you that the more complex your for statement is, the less understandable it is. The usual use of a for statement is to start at 0, go up to some value. This executes 10 times. Executes x equals 0, 1, 2, 3, 4, 5, 6, 7, 8, 9. And now what do we want to do? Let's just print x. So this is going to print 0, 1, 2, 3, 4, 5, 6, 7, 8, 9. Thank you. For statement is used to do iterative stuff. You want to do something a certain number of times. For example, you have an array that you want to set to 0. You go through the array. Array is a kind of variable that has multiple addressable locations. It's, you say you want something to be an array with 10 locations. You now have, and that array's name is number. So now you have number 0, number 1, number 2, number 9, and you can set each of those. It's a good way of remembering things that all go together. Iteration is the way we do things a fixed number of times. So one last control structure that gets used in this course is called the switch or case statement. And it's used where you have to compare a variable to one of several different values and do something different depending on its value. So suppose we want to take a variable x, assumes x has already been declared. So we take a look at x, and depending on what x is, we want to do something based on it. So we say switch, that's the name of the control structure. And then we say case 1, colon, sorry, not semicolon. So we compare x to whatever the case value is here. And if it's true, we do whatever's underneath the case statement. All right.
Question?
Yep.
Why can't you do, is this just an alternative to like using if-else statements? Because
yes, it is. You could always use if, because you can also do an if-else, 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 if-else. You do not want to have multiple if statements. It's ugly and it's hard to figure out. This is a much better way to do it. We're going to use the case statement. Now, here's what happens. Case switch x says, is it 1? Let's do the statements that are under here. By the way, it will continue to do all the statements all the way down to the closing bracket. If x equals 2, it will do the statements under case 2 all the way down to the closing bracket. If case equals 3, if x equals 3, it will do all the statements down to the closing bracket. If x does not equal 1, 2, or 3, it will do the statements under default. Normally, that's not what you want. So you will almost always see this structure like this. Break says, when you hit break, you are done with this construct. So if x equals 1, you do the statements between the case and break. If x equals 2, you do between the case and break. If x equals 3, you do between case and break. And we will almost always see the switch structure looking like this. Default is there because you don't expect it to do the default. You've made a mistake, and somehow x is a value you didn't expect. So oftentimes, the default will be print be something like that. Here's a function called print that prints somewhere, and it says whoops, x is, and it prints the value of x. We don't expect that to ever happen, but by putting the default in there, we catch it. You do not have to have a default in there if you don't want. But it's a good idea because it means that something you didn't expect happened. Switch is what you're going to use rather than if. You can use if else, that's fine. But if you find you're doing if something, else if something, else if something, else if something else, you're much better off using a switch statement. It's just easier to read. I know that if x equals 1, this is what gets done. If x equals 2, this is what gets done. If x doesn't equal any of these things, default gets done. You normally want a break after every one. Sometimes it turns out that you actually want, if x equals 1, you want to do some stuff, but also case 2, and then you'll take this out. That's hard to understand, and I would try to avoid that. In general, you want to write switch statements so they do exactly one thing for each value of the variable. But a switch statement is much easier to understand than this. For one thing, notice this has multiple levels of brackets, and you have to figure out what bracket goes with what. This only has one set of brackets for the whole switch statement. So I much prefer a switch. It's much easier to understand. All right, so let's see. That's most of the control statements. One statement that we're going to use a lot, and let me just take a look at another program to remember how I did it. All right. One of the things that's tough about using the Arduino is there's not much debugging facilities. There's no way to see what's going on. You have this LED, so we'll often use the LED just to tell us we got somewhere. What we'll do in setup is we'll turn the LED off, and if we get to a particular place in our code, I run our code and it doesn't work and we can't tell why, we'll go somewhere early in our code and say turn the LED on, and if the LED comes on, we know we got there. Or if something happens, we'll turn the LED on. The other thing you can do is there is under Tools a serial monitor that opens up a window that you can talk to. So let's go ahead and show how that might be done. Let me go up, and we got our setup. So here is a function. I want to know what it's doing. I have a variable that I'm changing. So I can output to this serial terminal using a library, and that library is called the serial library. It's built in. So what I need to do is in setup, I need to start that library, and I do that with a serial begin. So when you're using a library, the way you use it, the library's got some functions in it. You say serial, that's the name of the library, period, name of the function. Because begin wouldn't tell the Arduino environment where to find the function. You could have, the wire library could have a begin function, the serial library could have a begin function. You say the serial library period begin, and 9600 is saying how fast to send data, and it's a good value. Now I can use a function called serial print line. So here's my loop. Let's say what I'm going to do is I'm going to increment my variable I. I set I to 0 up here. And then I'm going to print the value of I. You can print text by putting it in quotation marks. But I'm just going to print I. There's two functions that are useful. There's one called print and there's one called print ln. The difference is one does a carriage return, one doesn't. I'll show you why that's useful. Now, if I print this, it's just going to output I very, very quickly. It's going to be running full speed. So I want to slow it down. There's a function called delay that takes a value in milliseconds. So this is going to increment I, print it to my serial print, and then it's going to wait 1 second, 1,000 milliseconds, and do it again. So let's go ahead and compile this and make sure I didn't make a mistake. If I get white is good. All right, so now let's download it to my processor. Okay, so it's downloading to my processor. Now, let's take a look at the serial monitor. And notice that it's every second, it's incrementing the value of I, and it's printing the variable I. That's a great way to debug your program. Now, the only problem is if the program crashes before it gets to the serial print, you're not going to know what's going on. That's where flashing the light is. Now, let me show you where you use print line versus print. Suppose I don't remember what variable I'm printing because I'm actually printing lots of different things. I can use the function serial print Now this will print, but it won't do a carriage return. So the result will be the following. I download that, takes a few seconds. Notice down here it says uploading. When it says done uploading, my program's running. I can open the serial monitor. And now It's telling me what it's doing. If I had used serial print line in both, it would have said the value of variable I is carriage return 5 and then carriage return. So using serial print means that I can put multiple things. And this is, I'd use this all the time. And in fact, I can do something like this. So now what I've done is I've printed the variable I is. Notice I have an extra space here so that there's a space. Then I print I, but I print it without a carriage return. And then without a carriage return, I put a comma and a space and then print another variable. And then finally, when I'm all done, I use the print line. And now I can look at two variables. I usually wouldn't be as wordy, by the way. I'm just doing that here because I'm showing it as an example. We open the monitor, and now it's showing me the value of two different variables. Notice I'm incrementing I, but I'm not changing K. So that's how you debug on this. You debug by using print and turning the LED on and off. If you can't get it to print because it's not getting to where you want, keep moving your print statements earlier in program. Typically what happens is you can have an infinite loop. If you do something like this, there is another statement called while. This is one I don't expect you to use. Whoops. The while statement executes while the variable, the parentheses evaluates to true. So as long as whatever's in this parentheses is true, we do whatever's in here. This variable is always true. If I execute this, this program just stops in this statement and stays there forever. This is a hung program. If I send this to my computer, I don't get anything. That's very frustrating. If I'd opened this early enough, I would have gotten it the very first time. This might be one where I want to turn the LED on or off if I get somewhere just to know how far I got. Maybe I want to turn the LED on at the end of setup just to know, did I do something wrong in setup? Or maybe turn the LED on, toggle the LED on and off every time I go into loop. There's a lot of debugging strategies we can talk about later, but using print and the LED are good ways to figure out what your program is doing. Because unlike more powerful environments where you literally can stop your program and look inside to see what all the variables are, that's not available in Arduino. All right, so that is my introduction to programming. Questions? Now, what I would suggest you do is hook up your Arduino to your PC, get the environment set up, and then over here under File, there is something called Examples. There's a bunch of built-in examples. The first one you want to try is Blink, because that works with no extra hardware. Some of these others, like Analog Read, you need to connect something up. You can look at some of the digital ones. They require you to connect a button up. You have a button. You can do that. So if we look at button, consists of a light emitting diode connected to pin 13. That's already connected. When pressing a button attached to pin 2, well, you have a push button. You can put your microcontroller into your breadboard, connect a push button between pin 2 and ground, and it's telling you how to do that. And then you can look at the code, see what it does, and start making changes to the code to make it do something different. Notice that it's using the button pin as input. This will not work unless you add a pull-up. So this should have input pull-up as the correct code. But you can look at the code and see what it does. So I would play with some of the examples. Try writing something. So you have a push button. You also have some LEDs. If you want to drive an LED from an Arduino pin, you can, but you need a series resistor. You need a resistor that limits the current. I've given you a bunch of resistors, I think around 400, I think you have a 470 ohm resistor in there. That's about the right value. That limits the output to a milliamp or so. So you can put the pin through the resistor and the LED to ground, and then when the pin is high, the LED will come on. When it's low, it's off. You can do it the other way. You can hook the LED to plus 5 volts through a resistor to the pin, and when the pin's low at 0 volts, it'll come on. So you can play a little bit, but you want to get a little bit comfortable with the idea of writing code on the Arduino. Okay?
Good.
Any
Thank
other
you.
questions before we say bye? All right, you can always ask on Piazza. All right, see
Thank
ya.
you.
Thanks.
Thank you.
See ya.